All right, so hi and welcome everyone to our exercise course, the number 6. So accordingly, we are talking about the exercise sheet number 6, where we have the topics. First of all, we want to look at a couple of properties of alpha strongly convex functions and also beta smooth functions, which come might handy for us later on. And well, since in the lecture 2 weeks ago, no, not the one today, the one 2 weeks ago, we have introduced the accelerated gradient descent, which is some kind of gradient descent with a more sophisticated momentum term. Let's put it like that. We will also talk about the accelerated gradient descent. So let's start with the first exercise, where we have exactly these two topics of alpha strong convexity and beta smoothness. And the first thing we want to show is the following equivalence, where we assume throughout the exercise that our function we are interested in, f, which is mapping from some solution space, theta, doesn't matter, some subset of Rd. This is a convex and differentiable function. And differentiable is important, and also, of course, convexity later on. And now, the first equivalence you want to show is that if f is strongly convex, then this is equivalent that this function g we specify here, which is nothing else than f theta, and we subtract from that the norm, the squared norm of the input times alpha half. This is a convex function. Yeah, and the other way around, if this is convex, this function g theta, then this implies that the function f is alpha strongly convex. All right, so we have our assumption. F is differentiable by assumption. So this already implies that g, this function g we have here, this is also differentiable because it's essentially a sum, or rather the difference between two differentiable functions. F theta is differentiable and the squared norm is also differentiable. So we can be sure we can compute a gradient of this function g. And what is the gradient? Well, simply implying or applying the sum rule for gradients calculations. So gradient of g is gradient of f theta and the gradient of the squared Euclidean norm. And well, by now you should already know this, but nevertheless, theta squared is nothing else than theta times, or inner product of theta with theta itself, and the gradient of this thing here is 2 times theta, yeah? So the multivariate extension, so to speak, for the quadratic function. And well, the 2 here in the denominator with the numerator 2 from the gradient are canceling out, so we are left with the alpha. All right, so g is differentiable and we have the gradient is given by that. What we can use is, if we start with the assumption that this function g theta is convex, plus we know g is differentiable because f is differentiable, then we know convexity. If g is convex, this is equivalent to the first order characterization we have here. Now, the first order characterization of convexity for g. This is what we use here, which we can use because g is differentiable. Now, otherwise we need to use here a subgradient, but no. All right, so first order convexity, stating that the first order Taylor approximation is always underestimating the function g for every theta prime, and theta prime is varying, and we can also play around with the constants more or less of the linear function corresponding to the first order Taylor approximation. Now we do nothing else than simply plug in definitions. Yeah, so by definition, we have g theta is given like this. So we have here on the left-hand side, simply plugging in the theta prime. On the right-hand side, we do the same with the theta. We use that our gradient of g has been computed, which is here. And then once again, the theta prime minus theta stays untouched. We haven't done anything. All right, then we have only to more or less play around with the terms occurring here. We want to arrive at the definition of alpha strongly convexity. So to arrive there, it's a good idea that this f theta prime stays on the left-hand side and everything else, essentially this squared Euclidean term of theta prime times alpha half, this should go to the other side. And if you do this, where is this term occurring? We have it here. What we also did was this minus alpha half theta, or squared Euclidean norm of theta, is here at the end. We have used the law of distributivity for this blue term, meaning that we have decomposed it into this thing and this thing. This is what you see here. And we have decomposed it also in this here, again with the same thing. And you see it here. No? So you see this is indeed still equivalence, what we have done here. No? Okay, then we look a bit more closely at these terms. So let's see on the right-hand, so on the left-hand side is how we want it. We don't touch the left-hand side anymore. The right-hand side, well, f theta is also something we want regarding definition of alpha strongly convexity. This here is, in fact, also something we want, this green term. So all we need to do is to say something about the rest. So this black box term, this blue term, and the one we haven't here encircled somehow. And well, if we now consider that this blue term here, this blue term is nothing else than alpha inner product of theta with theta prime plus alpha theta prime with theta, which is, as we saw just a minute ago, nothing else than the squared Euclidean distance of theta. So we can combine this second term from the blue term with this thing at the end, with this minus alpha half term, and we get here a plus alpha half term. This is where this is coming from. The first term is here, so the first term from the blue one is still here. It's still here, and the other one was combined with that one, leading to this. But now everything is as we want it, because now we have exactly the term we would like to have, namely this here, these three terms, we can collect them together to alpha half Euclidean distance between theta and theta prime squared. So if we look at this, so alpha theta minus theta squared, if we exit out, what do we get? theta minus theta prime. Perhaps I should have used something different as a color, but well. You exit out, you get alpha, the squared Euclidean distance, or the squared norm of theta. You get 2 times the mixed term. You multiply it with alpha half, so the alpha remains theta t, theta prime, and well, at the end you also get the squared Euclidean norm of theta prime. Now, this is exactly what we get here. And, well, everything together is giving us exactly the inequality of alpha strongly convexity. Now, so what we end up here with is this inequality, which is true for all theta, theta prime, which is exactly the definition of alpha strongly convexity. So equivalence is verified. If this function g is convex, then this is equivalent to alpha strongly convexity of f, which is nice. Yeah? So we will make use of this equivalence, in fact, because you can imagine alpha strongly convexity, yeah, dealing or verifying such an inequality is rather cumbersome, but showing convexity of such a function, yeah, is easier because we can use the second order characterization, meaning that we only have to show that G, or the Hessian matrix of G, is positive semi-definite. Now then we have verified convexity. All right, then let's have another implication of alpha strongly convexity. Namely, this is the so-called PL inequality sometimes, yeah, which is implied by alpha strongly convexity. Namely, that the squared Euclidean norm of the gradient at some point theta multiplied with 1 over 2 alpha is always an upper bound for the difference between f of theta and theta prime, yeah, where theta prime is the minimizer of our function of interest, or one of the minimizers. And it's a quite nice inequality because you can, yeah, if you look at the right-hand side, this is exactly, or such terms are of interest if we analyze different types of gradient methods or gradient-based methods, where we want to bound somehow the difference between our current iteration, yeah, so theta would play the role of our current iteration, and we compare it to the objective function evaluated at the minimizer. And then all we need to do is say something about the gradient, the squared Euclidean norm of the gradient at the iteration, which is more or less then the starting point how we do the analysis. But okay, so this is only for the background, why this is a nice inequality of interest for us. Let's see how we can prove this. So the definition of strongly convexity, we just saw it before. Yeah, so the function of interest is alpha strongly convex if this quadratic function with respect to the theta prime, if this is a global it's globally underestimating the function value f theta. Yeah? So we always imagine our function f is bowl-shaped, and this thing here is also bowl-shaped, and it's always staying under the graph of the f, yeah? Under the function f. All right, how do we get to our seek inequality? We simply minimize on both sides. First, we start with the right-hand side. Now, so if we minimize on both sides, the inequality is still maintained. Yeah, we don't change anything here because we can simply plug in some value theta star at the end. So for theta prime, theta star, this inequality is true. Then we lower bound or minimize this lower bound, and then the resulting thing is still a lower bound. This is the argument. Let's give this argument, or this right-hand side, simply a new notation. We call this f tilde at theta prime, which is nothing else than this quadratic function with respect to the theta prime. What can we say about this function? First of all, it's a convex function, right? So it's a quadratic function, so it's obviously convex, and we can also compute its gradient. It's quadratic, so differentiable infinitely often, and in particular also the first derivative exists. What is the first derivative? Well, with respect to theta prime, so here we take the derivative with respect to theta prime. This term here is a constant with respect to theta prime. This here is a linear term with respect to theta prime, so only the slope remains, which is the gradient of f at the point theta. And here, well, quadratic term, by now we should know by heart how to compute the gradient of such a quadratic term. It's simply 2 times the term, and therefore the 2 and the exponent, which is coming from the gradient, they are canceling out. Now, how do we find the minimizer of a convex function? We set the gradient to 0 and solve the equation with respect to our variable, namely theta prime in this case. And, well, set this here to 0. And this is what we want. Now, if you plug in theta prime this here, what do we get? Theta minus theta cancels out. Minus gradient gives us plus gradient divided by alpha. The alphas are canceling out. Oops, is there plus? There should be a plus, right? So if we plug in here theta prime with a plus, then the gradients are only canceling out, not with the minus. With the minus, we would get 2 times the gradient. Sorry. Yeah, okay. Good. Then let's see. I have adopted there will be somewhere an issue, but let's see. Let's plug in this value theta prime into our quadratic function, this orange one. All right, f of theta does not include theta prime. Then we plug in here for theta prime this one. And then we would get here actually a plus for the theta prime. Yeah, because plugging in theta prime, the thetas are canceling out. The gradient of f divided by alpha remains, which is multiplied with the, or multiplied in the inner product sense with that. And then plugging in here the theta prime does not change that. Wait, is there something is afoot here? There's something wrong. Where can be the error?
which part are you looking at? I'm a bit lost in the equations. Which part?
Yeah, so this theta prime, this here is
this minus or plus?
Yeah, this should be
a plus.
Should be actually a plus, but then this is not
from the equation right above, right?
Yeah, so this is, I mean, it's obvious that if you have it in this way, then the minimizer is that one. Yeah, this is for sure. But then
you need a plus.
Yeah, then we need a plus, of course. Sorry, I deleted it. But then the rest is not working because we get here plus plus, but here should be actually a minus. Why? To get the result. I mean, there is something wrong.
There is something in the squared Euclidean norm at the end of the equation. Because if you plug in a plus there, then you end up with 2 times theta inside the Euclidean norm.
Here you mean?
No, there's minus.
Yeah, so in the Euclidean norm, it's no problem. I think the problem is rather here, that here should be a minus. Because here, yeah, this term, this is the issue. This here is that one, and the gradient of that one, yeah, we get here a minus alpha half. A minus alpha half if we have it in this way, because it's the this is I was I was looking at the theta, but here we have a theta prime, and we compute the gradient with respect to theta prime, so here should be a minus. So here the minus reappears. Yeah, so with the minus everything is fine. Theta prime is the minimizer, or is the solution for this equation, that the gradient of f tilde is 0 if and only if theta prime is of exactly this form. Yeah, so plugging in the theta prime here is exactly giving us the 0 vector. Okay, now it's fine. And plugging in the theta prime, the solution we get, yeah, this is now having the right sign. Here, for the squared term, plugging in the theta prime, yeah, as this solution, theta minus theta cancels out. What remains is gradient of f theta divided by alpha. This is what you see here. The minus doesn't matter in the norm. We can forget about it. And well, here, this thing here, inner product of the gradient with itself, is nothing else than the squared norm of the gradient. So what we have here is minus alpha times the squared gradient of f at theta. Here we have 1/2 times 1 alpha. Yeah, so here the squaring. If we plug this, or we write this in front of the squared Euclidean norm, we have to square it. So you have here in the denominator an alpha one time. Yeah, so 1/2 alpha. Here, these two things here gives us a minus 1/2 times alpha of the squared gradient. Now, so this is the minimizer of the right-hand side of the alpha strongly convexity equation, yeah, of this orange term. This is the corresponding value. Now the left-hand side well, what's the minimizer of the left-hand side? It's the theta prime, the value where, or one of the values where it is minimal. And we get, well, left-hand side minimizer is smaller than right-hand side minimizer, and evaluated these things at the corresponding point is giving us this one. We rearrange this, we rearrange this. We bring this thing here on the left-hand side. We bring this here on the right-hand side. We get this one, what we wanted to show, so the PL inequality. All right, good. Then this is it for alpha strongly convexity, but we have another interesting property which we use all the time, namely that of beta smoothness. And for beta smoothness, we have in fact something very similar. We have also, or we can derive a quite convenient tool to check beta smoothness of a function by the help of some auxiliary function. And the auxiliary function here is this function h, where we now subtract the function f of theta from the Euclidean's or squared Euclidean norm of the input times beta over 2. Quite similar, only the arrangement is a bit different, which is due to the beta smoothness inequality, of course. So in the alpha strongly convexity, we have an underestimation, so the inequality is a lower bound, more or less. In the beta smoothness case, it's an upper bound, so it's in the other direction. All right, then the arguments are very similar to what we had before. So first of all, h is differentiable, obviously, same argument as before. F is differentiable, squared Euclidean norm is differentiable. We can compute the gradient. Gradient as before, beta, or very similar to as before, beta times theta minus the gradient of f. And once again, we start with that h is convex. We know that h is also differentiable. So the first order characterization is implying that this here holds true. So the first order Taylor approximation of h is an underestimation of h. So this linear term here on the right-hand side with respect to the theta prime we have here is globally underestimating the function h. Now we plug in definitions again. So this here is exactly this. This here is exactly this. And finally, we also use our gradient we have computed, namely that this thing here is this. Now we rearrange a bit these things. The minus f theta prime is actually something we want, because in the end, if we multiply the whole inequality with the minus, then f theta prime is on the left-hand side. This greater than or equal gets to less or equal, which we need for beta smoothness, so this is fine. So, as before, we bring the one term which is not useful for our purposes on the right-hand side. It's reappearing here. We once again have this and this, which is here. We have minus f theta with this appearing here. So these two terms on the right-hand side are already looking quite good. So only the remainder term is somehow not what we, or still not what we want. but again, making the same arguments as before, yeah, so this green box here is this, if we write this more in detail, so it's the inner product of theta with theta prime times beta minus beta times the Euclidean norm of theta. This here, yeah, so this term here, which we have, this can be, which we get from here and here, this can be computed together with this Euclidean norm term we already have for theta, and we result in minus beta half of the squared Euclidean norm of theta. The remaining things are the same, and then if we look again very closely, we see, yeah, so here I just make a more or less same colorful hint with the rainbow colors. Yeah, what I did before with the rainbow colors will give you exactly that this minus beta half squared Euclidean distance between theta and theta prime can be written as the difference, or the sum, however you want to call it, of these three terms. And we end up with the definition of beta smoothness if we multiply with -1 on both sides. And why is this really the definition of beta smoothness, or rather the definition we have, the equivalent definition if we have convexity? This is something we will talk about in a minute. So if this function f is convex, then this is an equivalent definition for beta smoothness. Yeah? So the beta smoothness definition is, in fact, a different one, where we have that the gradients are beta Lipschitz. So let's have a look. F is globally overestimated somehow. This is how you can always memorize this. It's always overestimated at any point by this quadratic term here, yeah, with the right beta coefficient for the squaring term. Okay, then comes the toughest exercise on this exercise sheet. Yeah? This is why we also have here a hint how to proceed with this. So in fact, beta smoothness is defined for a differentiable function, as I just said. Yeah? A differentiable function f is beta smooth if we have that its gradient is beta Lipschitz continuous, meaning that the Euclidean distance between the gradient of f at any two points, theta and theta prime, is always bounded by beta times the distance between the two terms, or the 2 points we plug in. Yeah, so you remember this double cone property we had for beta Lipschitz continuous, which is more or less specified by inequality 1. And only if the function is convex, this definition is equivalent to what we have here in blue, only then. So this is what we more or less used all the time, yeah, because we had in addition also strongly convexity, which implies convexity, and then this was fine. But here we want to show, well, if we have beta smoothness, then we also get this inequality. And this is a bit tricky to show, yeah, to be honest. Yes, this is why the hint was given here. First of all, yeah, this was more or less the the tricky part, namely expressing the difference between f theta prime and f theta as an integral with the fundamental theorem of calculus. And well, we can express it in this way. Yeah? So first of all, what is so perhaps a side remark, fundamental, so if you have f differentiable, then you can always express fb minus fa as f of the gradient of f theta, or the partial derivative in the univariate case, where we integrate from a to b. Now, this is what the second part of the fundamental calculus, theorem of calculus, is telling us. This one. And now the question is, well, how do we use it? Again, this was the tricky part. So my claim is the difference between f evaluated theta prime and f theta can be expressed by this integral, which is coming from the second part of the fundamental theorem of calculus. Why? Well, let's define the function gt, which is f theta plus t times theta prime minus theta. And we define this function from 0 to 1, for r. This is the function g. It's a univariate function, so you plug in a univariate value between 0 and 1, and you get something real valued, because f is mapping it to a real value. All right, what's the derivative of g with respect to t? And this is something we had in the lecture today. We applied the chain rule. So first of all, the outer product function, or the outer function, which is f, for which we plug in the inner product, or the inner function, right? And we get this here. And then we have to multiply this with the and then we multiply this with the derivative of the inner function. And the inner function is theta plus t times theta prime minus theta with respect to t. This here stays the same. This here stays the same. I knew it. This won't work. Okay, then. Don't be lazy. The prime minus theta. And what's the derivative of this function with respect to t? It's, sorry, here's an inner product, of course, or transposing missing. Here again. And we get here multiplied with theta prime minus theta. It's a linear function with respect to t, so only the slope remains, more or less. Okay. If you look at this, so this is our function g of t, or rather its partial derivative. This is what we see here. Or at least I want to show here. Okay. Yeah, so you followed all of this. This is the partial derivative of g with respect to t. Now the question is the left-hand side really... Yeah, so this should be then g evaluated at 1, and this should be g evaluated at 0. But this is indeed the case. If we plug in g for t a 1, here for g, what do we get? We get f evaluated at theta plus theta prime minus theta. So the thetas are cancelling out, only the theta remains, and evaluating g at 0, yeah, what remains is only the theta. So this is indeed the left-hand side. So you see, this was indeed the tricky part, how to use here the something went wrong here with the encircled things. Sorry, I don't know what happened here. Because I guess this was due to my copy-paste mechanism maneuver. Okay, so we have expressed this as an integral, which we can use at this point as we want. Yeah, so in red, this is our brilliant idea. So we apply it here and express here the difference as this integral. The remaining thing, don't forget about the minus, is here. Inner product of f evaluated at the gradient with theta prime, the difference between theta prime and theta. This thing here is in turn, or we can express this also as an integral, because we can multiply here with the 1, and we can multiply with the following one, namely the integral of the one function from 0 to 1. It's a 1. This is giving you a 1. This thing here, this in green, this is a constant. It's not depending on the dt somehow. So we can also write this inside the integral so that we get that one. So we can write it as the integral ranging from 0 and 1 of this constant term, which is not depending on dt, multiplied somehow with the 1 for which we do the integration, and this is it. And now we can collect these two integrals. So we have a difference of integrals. The integral is a linear operation, just like the sum. So we can collect or use law of distributivity. And we can also see, okay, here and here we have the same terms. So we can collect it quite conveniently here and write it as the difference between the two terms which are different. Then, yeah, this is a bit now unlucky. Because this is, of course, an image, and then it's always very hard to get rid of these things. Okay, I will simply delete it. This is my fix here. And so we are convinced that this is the partial derivative. Okay, then from here, we can simply apply absolute value on the right hand on this side. We make this only larger or equal. If it's positive, it's equal. If we apply absolute value, we make it only larger. Then if we write the absolute value inside the integral, we also make it only larger because we are then potentially only integrating over something positive throughout the time here. If the absolute value is outside the integral, it might be that in this integral we are integrating over something which is negative, and we only make it larger if we make it positive with the absolute value here. And now what we have here is more or less a vector x, yeah, and a vector y, and their inner product. And Cauchy-Schwarz is telling us that the absolute value of the inner product of any two vectors, doesn't matter, is always smaller than or equal than the product of their Euclidean norms. And this is what we get here. This is our Euclidean norm of the x vector, or what we called the x vector, and here the Euclidean norm of the y vector. And now we finally use our beta smoothness assumption, or beta smoothness definition, which is originally stated as the gradients are Lipschitz continuous, so the difference between the two is always bounded by the Lipschitz constant and the difference of the input. And well, we see here, this is the difference between the two gradients evaluated at that point, this here, so that this Euclidean distance between the gradients is smaller than distance between their inputs. What's the difference between the inputs? Well, theta plus t times theta prime minus theta. The theta is canceling out. We are left only with t times theta prime minus theta, which you get here. And of course, don't forget the Lipschitz constant beta we have here. Okay, and then we have here the t, which we can write in front of the Euclidean norm. We have then 2 times the same Euclidean norm, so that we get the squaring here. This, and this are not depending on the integration variable, only the t here. So we get here beta times squared Euclidean distance between theta prime and theta times integral from 0 to 1 of t. This is 1/2, yeah? And we get the 1/2. So, long story short, we started with this here. We have proven that this is bounded by this term here. Yeah, so you see this was a bit tricky, but now we have finally a proof to use without a bad conscience that this definition, or we can also quite conveniently always use this inequality if we talk about a beta smooth function, where again, the original definition is via Lipschitz continuity of the gradient. All right, well, the lower bound is quite obvious in this case, because we have convexity. Okay, then finally we also want to have something like a counterpart of the PL inequality, which is implied by alpha strongly convexity. Here we get something very similar, and the derivation of this thing here is in fact very similar as what we did for the PL inequality. So we start with the beta smoothness inequality we had, we just have shown, or which we can also conveniently express like this, as we always do, and do again minimization on the left-hand side and the right-hand side. Again, The inequality is preserved if we do this. We can again, I will go over it a bit quicker because this is essentially the same what we did before. Yeah? So for the right-hand side, we introduce a new function, f check is it now, with respect to theta prime. Sorry. Thanks. Theta prime. Here again, computing the gradient, setting it to 0. Don't do the sign error as I did before. Will lead you to theta prime being more or less the same minimal value as before, only with the alpha replaced by the beta. You plug it in, you get, so this minimizer is plugged in into the function you minimize, and you get more or less the same function value. Again, beta replaces here alpha. You look at the left-hand side minimizer, which is theta prime. You rearrange it as you need it. This squared Euclidean norm of f evaluated theta on the left-hand side, f theta prime on the right-hand side. Voila, you have the inequality. All right, I guess this is fine for that. Okay, then let's have a look at exercise number 2, where we want to do now univariate optimization with accelerated gradient descent and gradient descent. So this is really something where we go over the concepts and check whether everything is fine. So this would also be something this would be a good candidate for an exam exercise, for instance, because here you go over the different concepts and can check whether everything is understood, and at the end you do some computation, simple computation of some iterations for 2 optimization methods. All right, so then let's see what we have here. We have a univariate function which is decomposed into 3 parts. The first part, a quadratic function, or a pure quadratic function, univariately when we are with a theta smaller than 1. If we are between 1 and 2, well, then this is a polynomial, so still a quadratic function where we also have a linear term, also a constant term. And when we are strictly greater than 2, we still have a polynomial, but with different coefficients. Then it's easy to, so we can check whether this function is continuous and differentiable. Well, it is. So plugging in the 1, we get here at the value, so for the limit case 25, and here 1 plus 84 gives us a 94 minus 24, 25. So they coincide at the boundary point. And for the 2, if we plug in the 2, you can check that this is also true, that everything is fine. Now, we want to show that this function is alpha strongly convex with the parameter alpha 2. And here, we make use now of our handy expression, or this auxiliary function g, which we introduced. So before, just a reminder, alpha strongly convexity of f is equivalent to this function here being convex. So in our case, we are now interested in alpha is equal to, we are in a univariate case, so the Euclidean norm is, the squared Euclidean norm is nothing else than squaring the input, and we get that one. So we only show that this is convex. How do we do this? We compute the Hessian matrix, this most straightforward approach. Let's have a look first what this g function looks like. So we have to subtract from f every time theta squared. Doing it in the first case, we get 24 theta squared. In the second case, where theta is between 1 and 2, the theta squared is gone, only the linear and the constant term remains. Third case, well, you already know what happens. The 25 turns into the 24 for the term of order 2. Then we can compute the gradient of this thing, yeah, so or first derivative. First derivative in the first case, yeah, so we can do this case by case. For the first case, theta strictly smaller than 1, yeah, the exponent is multiplied with the coefficient before, gives us 48, and we have one order, so we decrease the order of the polynomial by 1. Next case, we have a linear function from 1 to 2, linear function. If we compute the derivative, it's only the slope, 48 remains. Second case, yeah, here a polynomial with a linear term, constant term, the second order term as before, as in the first case, the linear term as in the second case, more or less, but with a minus. We compute the second derivative, or the Hessian matrix in quote marks, Hessian matrix of dimensionality 1 times 1. Here, first case, theta, so this is a linear function we have here, gives us the slope of the linear function. Here we have a constant function, a constant function with respect to theta, so we have a 0 as the derivative, and well, again, a linear function here gives us a 48. In all cases, we have strictly something which is, or non-negativity. This is rather 0 is neither. So it's non-negative what we get for all the values, and we know Hessian matrix, if it is non-negative, or positive semi-definite in this case for a 1 times 1 matrix, is equivalent to G is convex. The function you started with is convex, so we can infer G is convex, F is strongly convex with parameter equal to, because we set it here to 2 actually. Now we do the same, more or less, to showing that F is beta smooth, where we make use of the other quite handy result we had, namely that beta smoothness of the function F is equivalent to this auxiliary function with the beta parameter or coefficient here appearing. This is convex. Well, what we get for the function h is then plugging in the beta, so it's 50, dividing it by 2 gives us a 25 theta squared minus f theta. Then we don't have it here anymore, but well, in the first case it's 25 theta squared, which we subtract from 25 theta squared gives us a 0. In the second case, we subtract this thing from 25 theta squared, gives us 24 theta squared minus the rest of f theta, and well, for this case, we see 25 theta squared is subtracted from theta 5 theta squared, and this thing here remains with a negative sign, which we see here, 48 theta minus 72. Again, computing gradient, computing Hessian matrix, it's the same ingredient. You get, as the Hessian matrix, this case, so this decomposed function for the different cases. Again, it's every time non-negative or positive semi-definite. So the H is convex. H is convex, meaning F is beta smooth with this parameter. Okay, then what about the global minimizer of F? What can we say about that? Well, we look at the gradient of F. We compute it as before. So I should have copied somewhere. Just to make sure that I haven't done here some sign error or something like that. Yeah, this is why I want to have it here. Okay. All right. So, oops. There we go. This is the f. We do again, calculating derivative or gradient for each case. Case 1, theta's smaller than 1, we get here as a gradient 50 times theta. For the second case, between 1 and 2, we get here 2 times theta plus 48. And in the remaining case, 50 times theta minus 48. Everything looks fine. Yeah? Haven't done here some sign error. Okay, then how can we argue about the minimizer? Well, let's have a look at what the gradient is doing for the range between 0 and infinity. There we see that the gradient is always greater, strictly greater 0. Because plugging in something which is strictly greater 0, here in the first case, we get something strictly positive times 50, stays positive. In the other case, yeah, still you get something which is strictly positive for each of the values here and also here. Yeah, so for the range from 2 till infinity, multiplying something here with 50, which is greater than 2, subtracting from that 48 is still something which is strictly positive. So you see the gradient is strictly positive, which means that the function f is strictly monotonically increasing on that range. The same or almost the same argument for the range between minus infinity and 0. Minus infinity and 0, you get here, if you, so there only the first case is interesting, where theta is strictly smaller than 1. Multiplying here 50 with something which is negative, you get something negative, meaning that the gradient is negative, which indicates that the function f is strictly monotonically decreasing on that range. Finally, what is the remaining case? Namely, the remaining case is the point 0 itself. We plug in the 0 here. We get for the gradient that this is a 0. So there is a critical point. Well, collecting the two, we have strictly monotonically increasing behavior right from the 0, monotonically decreasing behavior. Left from the 0, we have at the 0 that the gradient is 0. So this is indicating exactly at the 0 we have a minimum. Then finally, we do a computation for this function f. Namely, we compute how many? Until convergence. Until convergence, we compute the iterations for the gradient descent if we apply it for this function f, and Nesterov's accelerated gradient descent, where we use the optimal choice for the momentum coefficient. So let's start with the simple gradient descent method. As a starting point, we start at 3. We have for the step size, actually this is, what is this? This is 1 over 50, yeah? Which is 1 over beta, because we have shown before that the function f is beta smooth with parameter 50. This is where this choice comes from. We start with the gradient descent iteration. Well, from free, we go with step size 1/50 into the direction of the gradient at that point. We are, and now I would need, at point 3, we are in this else case. This is why we use here this one, plugging in for the theta, the free, calculating it by head, of course. Now, this is what we always do, but of course you can, so if necessary, you will use a calculator in the exam for such cases. And what you get is that the next iteration will be at the point 24, 25, which is strictly smaller than 1. Yeah? So now we are in this case with the next iterate. So we do the iteration again. Use now that we are in this case, plug in the gradient for that case, which is 50 times the input, 50 times the input. Well, you see this quite conveniently here, 24/25 minus the 50s are canceling out each other. The terms are the same, which remain. We have a 0. Well, then roughly or strictly speaking, you would need to run again a converge. So you wouldn't stop here because you still don't know whether this is the minimum. You only know it if your gradient is vanishing or your iteration is not, or equivalently your iteration doesn't change. So you do the iteration again. You use the case that you are strictly smaller than 1, and well, 0 minus 0 is a 0. You don't have a change in your iteration, so you would conclude it converged. You found the minimum, which is 0, and which is indeed the 0 for this function f we are dealing with. Now we do the same computation or similar computation with Nesterov's accelerated gradient descent. For convenience, let's again restate how the iteration looks like. Gradient descent we know now by heart. Accelerated gradient descent, we need to see it a couple of times perhaps. So it's given in its alternative form, which we derived in this way. So the next iteration is given by this yt vector, which is tracking the momentum term more or less, minus gamma times gradient at the momentum term. This look ahead gradient, and this look ahead gradient, or this yt, is composed of the momentum term and the iteration you had before. Now we have shown more or less that this function is gamma well conditioned. We have shown it's strongly convex, it's beta smooth, so it's well conditioned if it's both at the same time. What's the well conditioning parameter then? Well, it's alpha divided by beta. We have shown alpha is equal to, this is our alpha, this is our beta, so the gamma is 1/25. So the optimal choice for the momentum coefficient is the well conditioning number inversed. So in the lecture, I made this announcement that there was a bug, the inverse was missing. Otherwise, you would have here a negative momentum coefficient, which is strange, of course. But now, if we do the inverse thing, we get here the right value. The square root of 25 is 5. Here and here, you get as a momentum coefficient 2/3. 4 divided by 6 is 2/3. All right. Then we do the iteration via Nesterov Accelerated Gradient Descent. We start with the free as before. We have as our momentum coefficient 2/3. Well, we haven't specified it, but the very first, or the -1 step is a 0 then, simply that you get here as the look ahead position, the 5 with Nesterov's You plug in this look-ahead position y0 into the gradient descent-like iteration. You have again here the case that you are strictly greater than 3. Now, this was that we use this gradient, plug in the 5 here, calculated of course by head again, and we end up with the same iterate as the gradient descent, 24/25. We use this again to compute the next look-ahead position, the y1, plug it in, and what we get is minus 2/5, which is a bit over so we have jumped over the minimum when we come from the right, more or less. But no problem, because when we plug it in into the iteration, now we are now exactly in the same case as before, that we are strictly greater than 1. Plug this minus 2/5 into the gradient at that position, and we end up with the 0. Yeah, so this is correcting itself more or less as we want it. Again, you would need to do another iteration step. You again compute the look-ahead position y2, plug it in, you get minus 48/75. You plug it in into the iteration, nothing changes. You had a 0 before, you stay with the 0, you converged. Okay, yeah, so once again, this is a quite nice exercise. This is why I wanted to have it here, because it's representative for an exercise you can expect in the exam at the end. All right, so looking at the time, I seriously doubt that I will manage to talk about the practical exercise in the remaining 10 minutes. As I said, I have to leave a bit earlier today. So, no problem. I will record a video about how I go over the Python notebook, which I have prepared for this exercise, and then you can watch it later on. All right, so then, thank you very much for participating, for watching, and see you then next week. Have a nice week. Bye-bye.